Okay, well, welcome everyone to the return of our Center for Machine Learning and Intelligent Systems seminar series. Unfortunately, still virtual. We'll see how long we need to keep it in this format before we can return to in person. But nevertheless, I'm excited. We're going to have a great talk today by our very own Roy Fox, who's an assistant professor of computer science here at UCI. Roy was previously a postdoc at Berkeley and has been doing lots of interesting work at the intersection of reinforcement learning and robotics and information theory and machine learning. And he's going to tell us about some of his recent ideas in that space today. So please go ahead, Roy.
Thank you, Eric. Yeah, it's great to be here. Thank you, everyone, for joining. It's great to see your names in little boxes. But really imagining that you're listening, so thank you. And yeah, the title here is sort of a mouthful: curiously effective ensemble and double oracle reinforcement learning methods. And there's one word here that has a really important role, and that's the word "and," because it sort of connects to very loosely connected ideas. So it's really a lecture in two parts. Let's start and ease everyone in with just a quick background in reinforcement learning in case you don't quite remember what it is. So we have a system of an agent interacting with an environment. It's a sequence of decisions that the agent is making in interaction with the environment. It can really model a lot of real world cases of interest. Visual navigation, maybe a robot trying to navigate an interesting environment and do something there. Maybe managing infrastructure such as power grids or cooling of data centers and so on. And really exciting applications in robotics and other fields as well. So a lot of recent successes in this field. And so let's see what more we can say about it. We have the system that undergoes a state evolving through time. It's a dynamical system, and we get a chance, an opportunity to control it, to affect the state by providing input to the system, which we call actions, and they affect this evolution of states through the dynamics of the environment. And because we're an agent that is taking those actions, we have a policy by which we decide which actions to take. And so now there's this joint system of the agent and the environment. And our goal in all of this is that we're getting rewards for taking good actions, right? So someone is providing us a signal that tells us what our good actions were and what are bad. And so what do we want? We want high rewards. When do we want them? As soon as possible, please. So we're going to take the sequence of rewards that we might be getting in this interaction process, and we're going to sum them up into one scalar that we can optimize, but discounted by a discount factor less than 1, so that later rewards are not as valuable. Also, later costs are not as bad. And so we're going to call this a return, and it's the expectation of this return that we're trying to maximize over choice of our policy. So that was a crash introduction to reinforcement learning. Please, of course, stop me with any questions once it gets interesting. So a basic and celebrated algorithm in reinforcement learning is deep Q learning, DQN. So we have a Q function, that's the expected future return that we expect to get if we take action A in a current state S. So it's a function of the state and the action. And we can implement that using maybe a neural network that takes in a state, and if the action space is discrete, we output a Q value for every possible action. And so how to optimize this? Maybe we get experience, a state, and the action we took, and the following state, and the reward that we got. And so now we have a better guess for what this Q function might be. It's the one step ahead, the reward plus a discount of the maximum of the next Q value over the maximum over all possible actions that I'm going to take in the next step. And so our loss is the square loss between those two parts, the thing that we're trying to estimate and a better target for what it might be, And that's the square loss that we're trying to minimize. Now we're only optimizing over this term, not over the target term. And that will be part of the target network. I'm going to say something more about it because it turns out to be important. And then finally, when we have this Q function, we can find our policy. It's just a greedy policy. We take the action that just seems best according to our prediction of what the returns are going to be. So now one thing that's important in sort of considering in thinking about these algorithms is thinking about bias and variance. That's generally an important thing in machine learning, and this is not an exception. So if we have high variance in our Q value estimates, that means that we may be wrong when we're trying to choose an action, right? So if our value estimate is noisy, it's that's much more likely that we're going to look at the suboptimal action and it actually looks greedily optimal, and we take it, but it's really suboptimal. So we want to avoid that kind of high variance, but there's actually one more effective high variance in this case due to the Jensen's inequality. So when we're taking the maximum of our Q function for a target of the next step, it's actually biased. Because of Jensen's inequality, this left-hand side inside the expectation which we're using for the target is an overestimation of the right-hand side in expectation. So our target is really an overestimation, and it's going to be more of an overestimation the more variation or variance there is in our next step Q targets. So high variance also creates a positive bias in our updates, and a positive bias is no good. For one thing, it means that every time we update our Q value, we introduce a little bit of positive bias, so we are biasing ourselves to use that action more for no good reason, just because we updated it more. So we don't want to do that. The takeaway here is that in Q learning, variance generates bias, and that's a bad thing. Okay. So one reason to use a target network is precisely to avoid or to reduce that high variance, right? So if you look at the DQN loss, we don't take a gradient over this target term. What we can do instead is have two separate networks. One is our learner network at the top, and one is our target network at the bottom. We feed the state into both. We get our prediction from the top one and our target from the bottom one, and then we take the square loss between them. But gradients pass only through the top one. The bottom one is updated from the top one gradually, maybe by moving its parameters gradually with some coefficient lagging behind the top one. And so that lagging behind, that lagging copy of our Q network, updated like this maybe, means that it is more stable. It means essentially that it's less sensitive to the data that the learner is seeing, and so it has less variance. And that's a good thing, right? It stabilizes our learning, but there's a cost because it does introduce bias. Our target is not really coming from our own Q value, but it's coming from a different network that is lagging behind and so different, and so it's biased. All right. So let's consider other ways to reduce that bias. We can get inspiration from general machine learning methods. For example, bagging, which is an ensemble method where we average over K models and therefore reduce the variance, right? So if the models are kind of uncorrelated to some extent, or they're partly correlated, and so when we average them, the variance of their average is lower than the variance of each one. And that's very useful. Ensemble methods have been used in reinforcement learning, but for very different purposes. So let me give you some examples. So one very classic ensemble method that uses two models in reinforcement learning is called double Q. And that's when instead of taking the maximum from our target, what we're taking is we're evaluating our target, with an action that is the argmax of another network, maybe in this case, our learner network or prediction network. And so we're not using the same network for the argmax and for the evaluation, and that reduces the bias. In fact, it introduces negative bias. Another method that came out recently is called max-min, and that's where we're taking an ensemble of k-models, and we're taking their minimum before taking the maximum over actions. And that decreases the bias. The larger the k, the number of the ensemble size, the lower the bias until it gets negative. At some point, it's close to zero, and that's sort of the optimal ensemble size. Not very tunable, but it's a good method. There are also other methods. There are methods that are using ensembles for exploration. So if we have an ensemble of learners, we can estimate variance as a measure of our uncertainty about what we've learned. And if we have high uncertainty, maybe we want to have optimism under uncertainty and explore those states more. So this is not about the update of the learning of the Q, but about how we collect more data. There's also a recent method called Sunrise when where we downweight updates where the target has high variance. That means we sort of don't trust those updates as much, so we just give them lower weight and hopefully reduce the variance that way. And that's a very successful method. It sort of beats some state-of-the-art prior methods. But really what we want to do is really take inspiration from the way ensembles are used in machine learning, the standard way, and borrow that into reinforcement learning in order to reduce variance. So it's really a simple idea. We're really going to do the exact thing that that you would think about. We're going to learn an ensemble of KQ models, KQ functions. We're going to, whenever we need to make a prediction, we're going to take their mean. And so our update now is updating our Q function, our learner Q function for every model theta K towards the mean of all models. So we take the mean and then we take the maximum over actions the same way we would do anyway. And that's our update. So it's a very simple method. For the best performance, we can combine it with a lot of tricks that have been employed in DQN to achieve the state of the art, and we can employ them here as well. So there's a set of tricks called Rainbow. I'm not going to go into all these, but just here's a list of them, except one, that's double Q, which I mentioned in the previous slide. We don't need that because we're using the ensemble in a different way, but all the rest we are using. And also we're doing the UCB exploration I mentioned in the previous slide. As long as we already have an ensemble, let's use that also for better exploration. So those are the tricks we add to this very simple method. And well, if that's all I had to say, then it's sort of yeah, why am I telling you about it? Such a simple method. Well, I'm telling you about it because it's really, really, really effective and curiously so. I don't want to say unreasonably so because it's reasonable for this method to be effective, but we're not quite sure why. So let me explain what I mean. But first, some results. So one of the most studied benchmarks in this field is Atari. You have here at the top an example of screenshots of 3 Atari games. Played from pixels from these images, and it's a well studied benchmark. And surprisingly, this method outperforms existing methods. So here it is first without all the extra tricks, the rainbow tricks, and so on. And what we have here in blue and orange is just a plain DQN method with and without the target network, the lagging target network. On 4 example games. And we also have our MeanQ algorithm with in green and without in red a target network. And so we see that across these 4 domains, these 4 games, this new method outperforms the baseline quite significantly. That's cool. But also with the all the rainbow tricks, ignore the purple for now. That's sort of an advanced method we're looking into right now. But the red one is the new method, and it compares favorably with rainbow. Also, if we're trying to be more fair, maybe because we are having an ensemble, we are effectively having a larger network. Can we let the baseline have a larger network? We're also updating more often. Can we let the baseline update more often, and so on? All of these sort of charitable attempts to improve the baseline, some of them actually improve a little bit, mostly they don't, and we are still outperforming it. So it's a really good method for this network size and for this rate of updates from experience. We also compared to a bunch more algorithms that we didn't run ourselves. We just cited the results that they have in those papers. So those are the flat lines, just the value that they have at the rightmost amount of experience used for training. And so on some of these, at some point, we outperformed them. But you can see on the right an average from 27 of these Atari games. Normalized, so between 0 and 1, 0 is random behavior, 1 is human level performance. And already in, this is 100,000 experience steps. We are greatly outperforming these other algorithms. So we're pretty much state of the art. With 500 training steps, we have a different set of algorithms for which we know the baseline, so we compare against them. And an interesting thing to note is that already around 350,000 steps, I would say we outperform human behavior. Now, I should say this agent does not have memory. Some of these games really require you to have memory, an RNN or something like that, to perform well. We don't have it here. It would be tricky to train. There are dedicated algorithms that can do that. We're not comparing against them, and they perform much better. But in the category of agents that do not have memory, we're pretty much state of the art. So that's encouraging. So let's try to understand what's happening here. And really the story, as I set it up, is variance reduction. So the rationale is that if we can average a bunch of partially correlated models, we can reduce the variance. If we reduce the variance, we reduce the update bias. Maybe we even eliminate the need for a target network, and that further reduces the update bias because the target network is itself biased, right? So we get another boost there. And that's indeed what we see. We can eliminate the target network and perform even better because we don't have that extra bias. But now the question is, are we really using partially correlated models? Is that what we have here? Just how correlated our ensemble is? And I don't have a direct answer to that, but there's a lot of reasons to think that they're not as uncorrelated as we would like them to be. Ideally, fully uncorrelated. They're not. So first of all, we did not explicitly make any attempt to diversify them and make sure that they maintain their diversity and remain uncorrelated. On the contrary, we're training them from independent samples, yes, but those samples come from the same experience, right? So the way this works is that the trained agent so far interacts with the environment, collects data, that data goes into a replay buffer, just a big data set of the agent's past experience, and we sample from that replay buffer. So the samples are independent but the replay buffer is shared, and also the policy that was used to add data to that replay buffer is the same. So those are very correlated. Also, we are using the exact same target function. So we're training on different experience, sampled independently, but we're using the average of all ensemble members for each ensemble member to update. So it's the same target function. So they're really updating towards the same thing, and they become correlated very fast. And just to give you a sense of how that might look like, we don't currently have more direct evidence, but here's some indirect evidence that's just interesting to see. So if we look at this frame from the game sequence, this is just an ordinary frame from this game after a bunch of training. Maybe the target values look like this. So each row is an ensemble member, and each action is a column. This is a greedy policy. And so ignore the green curve for now. That's a different method that we're looking into. But look at the blue curve. It's now called MeanQ, not average Q, same thing. And you can see that it's a pretty narrow distribution. You can see a sort of Gaussian approximation of it, but the points here in blue is a distribution of target networks, target values from the different ensemble members. And so you can see that the spread is very small. But now we introduce a weird thing into our observation artificially. It's not in the game. We introduce a fish that moves vertically. That's a clever idea by Litty and Young. And this never really happens in this game naturally, right? So it's a little bit unusual. And so we expect the ensemble members to maybe disagree on it a little bit. And indeed, we see a larger spread of the Q values that the ensemble members predict. If we make things even more weird, there's a school of fish here that definitely never happens. Now the Q values are sort of even larger spread. And if we have a school of submarines, right? So that is just not within the realm of the game. We have a very, very large distribution. So what this tells us is that after training, for the states that we actually see in training, the ensemble members sort of converge on agreeing on what the correct Q value is. So you kind of expect that if they're just really good, but we sort of have indirect evidence that it's probably happening more than is justified. So it's not just that they're very good, they agree more because they were trained jointly, and they probably become correlated. So that's a problem for the whole premise of reducing variance. And there's actually also some theoretical things to worry about. As first pointed out by Alex Eiler, if we are considering linear function approximation, which theoretical RL does a lot of the time to be able to say something theoretical about this. So we imagine that we model our Q function as a linear function of some fixed state features, so not learned features as they would be in a neural network, but a fixed vector of features times a vector theta A for every action A. So just a linear function. By the way, this generalizes the special case of the tabular case, tabular Q-learning. If the feature vector is just one hot encoding of the state, you get tabular Q-learning. So it's more general than that, not much more general, but it is more general. And if we try to do our MeanQ algorithm with this linear parameterization, what we would get is that when we're taking the mean over the ensemble, and we write out what it means linearly, we can just take out the feature vector and just say that it's the mean over our parameters. And so if we're updating the parameters of our learner on the left, and we're only using the mean of the parameters on the right, everything is just linear in the parameters. And so this is really just equivalent to doing Q-learning with the mean of the parameters. So we're not really using the ensemble, we're just using the mean of the ensemble. We're never using anything other than the mean of the ensemble. And so this is not going to give us a benefit. If we want to see any benefit of MeanQ, we really need nonlinear parameterization. And now this is beginning to be interesting because this kind of goes both ways, right? We can say, okay, we don't maybe understand nonlinear parameterizations as well as we should. And if we did, maybe that would tell us more about how to do good deep reinforcement learning. But also the fact that we are having this success in deep reinforcement learning tells us something about the necessity of nonlinear parameterization, and maybe we can learn something about that. So I don't have answers, but I think these are really interesting questions, and let's add one more consideration to the mix. So let's talk about the diversity that we get with just the independent sampling from our replay buffer, from our experience so far. Is that important? Is it important that we actually sample the experience that each member of the ensemble sees independently from the replay buffer? What if, so empirically, yes, we tried it, it's not working as well, but why? So one answer is, yeah, just intuitively, it maintains diversity. If you have diversity, maybe they're partially uncorrelated, maybe you can reduce the variance. That's not very satisfying because it doesn't really tell us much more than that. So let's try to dig a little bit deeper into what's happening here. So what if we did update all ensemble members from the same data? What would we see? So let's make a simplifying assumption. I want to argue that it's not outlandish to assume that the Q value that each ensemble member predicts and the gradient in parameter space of that value function are approximately uncorrelated over the ensemble. Sort of like saying, the value that they predict and where they actually want to go in parameter space are not really that much correlated. The direction in parameter space. That seems somewhat reasonable, not perfect, but maybe. And if we just assume that, then we can approximate our update of the mean of the parameters by this expression here, which you can see only uses the mean Q. Sorry, this is a typo. It only uses the mean Q, not the mean theta, but the mean Q. So the mean over the ensemble. And that means that, again, under this assumption, all we're using from the ensemble is its mean. And if all we're using is its mean, then we're not really using the diversity of the ensemble in any meaningful sense. The fact that we do have an ensemble, we're just not using that. So again, what that means is to really leverage the ensemble in DQN, what we need is both nonlinearity of our representation and some sort of resampling that is uncorrelated between the ensemble members. And it's really the combination of these three things that gives us the success. And so they interact in some way that we don't fully understand. And that's a thing we need to study more. So just quickly, what we're looking at now, there's some connection between what I just said and dropout. So we're going to look into how the structure that we effectively have with the neural network interacts with this particular version of dropout. Maybe dropout is just a good thing to do in reinforcement learning, but it's just not what the state of the art usually does. And so in this particular case, it seems to be helping a lot. Why is that? What is the interaction there? We're going to try to understand that better. If diversity is so important, can we employ other methods to sort of maintain the ensemble diversity? Maybe we can trade off the variance reduction with diversity. And can we also combine this with existing methods to reduce the bias, because people have been looking into that. So there's some residual bias even after we use an ensemble. It's reducing the variance, and so reducing the update bias, but it's not eliminating it completely. Can we combine it with methods that do try to eliminate it? And finally, we actually started looking into continuous action spaces and there's sort of mixed initial results. Some of the methods we tried are, again, curiously effective. We don't quite understand why, but they're, again, working very well. So maybe I'll take any questions now before I move to something quite different, to a different project.
Hi, Roy. I have a question. So it's maybe an entry-level question. So I was wondering, at some point you mentioned that the bias, you want to reduce the bias, and you mentioned that there are some arguments that provides negative bias. But I was wondering why negative bias is a good thing, because like positive bias results in overestimate, which I understand is not good, but why underestimate is necessarily a better thing?
Great question. Yeah. So no one quite understands this. This is still being sort of studied. But here's my intuition here. So if we were to talk about exploration, about collecting more data, then there's this principle of optimism under uncertainty. So we want, it's exploration, right? We want to explore things that we don't know as well. And for that, it makes sense to introduce positive bias to those states and actions that we have not explored often enough. But what we're talking about here is bias in the updates. So that means that every time we update a state in an action, the Q of that state in action becomes unfairly a little bit more positive than it should, right? And so it's not the underexplored states and actions that get this bonus. It's the ones that are explored, or at least are updated often. And that's just not a good thing. But now if you introduce a negative bias, that means that those states and actions that you update very often, they get a slight negative bias. And so relative to ones that you have not updated very often, those get a bonus, and that's sort of an exploration bonus for optimism or uncertainty. Now that's a very inexact argument, because I'm sort of conflating here the updates and the exploration. They're really not quite the same thing. What we really want to be is unbiased in our value estimates, and then if we want to introduce any bonuses for exploration when we explore the environment, we can do that. But we should sort of separate that. But that's something that no one quite knows. No one really knows how to do.
Thank you very much for the invitation.
Can I also ask a question? I was wondering, in the initial slides, you show us a method that they use minimum of the K models, and then to reduce the uncertainty and the variance. I was curious, how does this MeanQ compare to the minimum Q?
So you're asking about the comparison between our method MeanQ and what's called maxmin, where they take the minimum over the Q
correct.
functions?
I mean, what?
That's a good question. So first of all, we're still positively biased, right? We're just reducing the variance, but we still have the same Jensen inequality. That means we're positively biased, but less so. They have the opportunity to become negatively biased, or maybe close to unbiased, if they choose the ensemble size just right.
Thank you.
That's one. I mean, there's plenty of points for comparison. Let's leave it at that.
Also, I had another question. There is I was wondering, how does it, because we have some term that it is federated learning, in which they average the models for improving the accuracy and predicting model. I was wondering, is it kind of like a federated learning with DQN, or is it the training procedure is different?
I have to say I don't know enough about that. I think what we're doing here is different. I think there's some sense of distributed computation in that sort of federated learning that we don't have here. Here we're talking about just one agent that is doing the optimization. There's no distribution of data or of computation or anything like that.
Thank you very much.
Great. Okay. So now for something, takeaways. Okay, yeah. So bottom line, Ensemble RL methods are surprisingly more effective than we actually thought, but we need more analysis to understand them better. So yeah, that could be said of a lot of RL methods. That's just the state of this field. So let's move on to something slightly different, or maybe a lot different. We're now going to introduce another agent into the environment. That's going to be an adversary. And the adversary is actually trying to cause the agent's rewards to be as low as possible, right? So this is a zero-sum game, sequential game, where and it has a lot of applications, famously playing Go and beating world champions, but that's just a game. But there's also a lot of actual applications for zero-sum games, although they're called games, but there's a serious thing. For example, if we want to do robust reinforcement learning, so we want to do reinforcement learning in a way that is robust to whatever the environment is going to happen in the environment that we may not know ahead of time, but we want to be robust to that. And so we can assume that there's an adversary that picks that worst case for us, and we want to do well in that worst case. And so we're looking into those cases as well, but I won't talk about it today. So those are environments where we have two agents taking actions. The rewards of one are the penalties of the other, right? So one is trying to maximize and one is trying to minimize. And what's not in the picture here, but is also important, and we will consider such cases, is when the state of the environment is partially observable. So each agent gets to see just some observation of the state and not the full state. And in that limited information state of what the real state might be, needs to take actions. So what are some sort of methods that people use to learn in these settings, in these domains? So the simplest one that a lot of people do is called self-play. And that's, okay, let's start with some definitions. So best response is when we just optimize our policy with the other player fixed. We just respond to whatever we think the other player is doing right now, a fixed policy, and we try to respond to that the best we can. That's a best response, BR. A Nash equilibrium is when neither player wants to switch. So both players have a best response to the other, and they don't want to switch to a different policy. That's a Nash equilibrium. And so self-play is when each agent best responds to the other's latest policy, current policy, right? Not considering any history, just responding to what it is right now. And it's very appealing because it can just be implemented with independent reinforcement learning, just learning with whatever the other player happens to be right now. So schematically, it looks like this. Here we have in red the history of player two's policies that they used. And player one in green is just best responding to just the latest one at the top. So you see in blue the sort of the distribution of where player one is sort of attending over the history of player two's policies. It's just the most recent one. This is 0. And likewise, player two is only considering player one's latest policy and only best responding to that, and not looking at the entire history. That's very easy to implement. Unfortunately, it does not converge. It's not guaranteed to converge to a solution, to a Nash equilibrium. It doesn't even do that for small games. The problem is that behaviors need to be stochastic. So consider, for example, playing rock, paper, scissors. Of course, we need to mix over all three actions so that we're not predictable to the other player. But if we're just best responding to the other player, we can just find the best action. It's not stochastic, and that makes us exploitable, makes the other player be able to beat us. That's not going to work. So let's try to do better, something more game theoretically justifying. So there's fictitious play. Fictitious play best responds not, so each agent best responds not to the latest policy of the opponent, but to the average policy so far. So this is the history of player two's policies. We just average over them and then best respond to that average. And likewise, player two best responds to player one's average policy, the average of the policies so far. This does guarantee convergence to a Nash equilibrium. Specifically, it's the average policy that converges, right? So the best response itself is just one action, the best action to take in every state. It's not stochastic, but the average is stochastic and it does converge to a Nash equilibrium. The issue here intuitively is that we average all past policies, regardless of whether they were bad or maybe they're just really outdated and it's not reasonable to play like that anymore. Both players are so much better right now, but we still average those past policies. So that's a price we can pay for having good guarantees that we actually converge, but we can have guarantees with something better. So that's called double oracle. And the way double oracle works is like this. So we have our population of best responses so far, or policies that we have so far. We find a Nash equilibrium in the restricted game restricted just to those policies, just those best responses, right? So we solve that restricted game, and then each player best responds to that restricted Nash equilibrium, right? So that equilibrium over population policies is what each agent responds to, and we add that best response to the population in every iteration. So it looks like this. We look at the history of policies for each player. We actually look at both policies and we create a big matrix and play them against each other and find the best mixture for every player, such that if they played that mixture over past policies, that would be a Nash equilibrium. And it may be a distribution like this. And that's what player one best responds to. And player two likewise best responds to the corresponding distribution over player one's historical policies. And now this mixture of past policies is guaranteed to converge to a Nash equilibrium. It's a different mixture in every iteration, but eventually it will converge to a Nash equilibrium, and hopefully faster, because we are allowing ourselves to give more weight to policies that are just better, we are just better off playing. Okay. When we go to bigger games, we can still do those things. With self-play, we can just play, run reinforcement learning independently. With fictitious play, we can just keep a running average of the policies. And with double oracle, we can do something called policy space response oracles, where the BRs are found using reinforcement learning, and then the restricted game over the set of BRs so far is solved as a matrix game. We just create a matrix of how well each policy is doing against each other policy, and we're just solving that game in its matrix form. The convergence property of this, well, one thing we kind of knew was that it's guaranteed to converge. PSRO is guaranteed to converge when all policies are added to the population. But that can be exponential in the number of information states. In fact, we tried it empirically to see if that ever happens, and it does. We can give a family of games that where theoretically we expect that to happen, but we also see that empirically. For example, in this game, where player one chooses between two rock, paper, scissors games, and then they both play it. So for player one, there's 6 possibilities, choosing one of the games and then an action to take there. For player two, there's 9, because they don't know which game they're going to play, so they need to pick an action for both. And when we run PSRO for this, we find that most of the time, indeed, we need to expand all 9 policies. So the entire population, even though it's sort of exponential and needlessly so. So can we do better? Can we sort of take into account the sequential nature of this domain to reduce the number, the size of the population that we need? The answer is yes. And that's an algorithm that we called extensive form double oracle, XDO. It's a very similar scheme to double oracle, to PSRO. And the main difference, so one thing that is the same is that when we're looking for a best response, we're just using any kind of reinforcement learning algorithm, same as PSRO. The main difference is that we have a different restricted gain. So in PSRO, the restricted gain is just a matrix gain over the populations of the policies so far. But that ignores that these are policies that are sequential. They make a sequence of decisions. So we're going to keep the sequential structure of the game. It's what's called extensive form of the game. And so our actions in this restricted game are going to be to choose a population best response, and we're sort of delegating to that past best response, past policy. We're asking it to take an action in the current state. So our action is to choose one of our past policies, and that policy is going to choose the actual action. Equivalently, we can think of the restricted game as just restricting our action space to just those actions that were taken before by any best response in our population. That's equivalent from a conceptual point of view. It's not equivalent computationally, and in practice, what we do is the first one. To solve this restricted game, it's again a restricted game in extensive form. It's this sort of sequential game, and so we need a solver for that. There's a bunch of solvers, and you can ask, okay, so why not use such a solver for the original game? Well, the point is that we hope that we will never grow a restricted game that is even remotely as large as the original full game, and we will only need to solve a much smaller restricted game ever. And so we can use existing solvers that cannot handle the full game, but we're feeding them only very small restricted games. That's the hope. And let's see how well that works. So in Leduc, which is a simplified form of a poker game, it's a small poker game. Our result is in orange here, and we are able to converge very, very fast, much faster than baseline methods such as PSRO, and form an extensive form of fictitious play. We also compare favorably with other methods that we can try to solve the full game. We also tried a game called Ashizumo, and eventually we sort of outperformed baselines, but it's not as significant, and early on we're less stable. So the conclusion here is that this is not always good. This is going to be good when we do have hope that we will only ever expand a very small fraction of the full game, because the best responses that we add to the population sort of focus us on actions that are actually useful to use in the final solution. And so if that's not the case, if eventually we will need to expand most of the actions, then this algorithm is just not going to give us a benefit. But one benefit that it does give is that it can handle games where the action space is continuous. So PSRO can do that as well. And if we discretize the action space, we can also have other baselines, such as NFSP here in green. But we significantly outperform those baselines, both in a two-dimensional sort of loss game that we define, or 16-dimensional loss gain, because we are able to really expand these populations in extensive form. So I want to say a little bit more about what that means. And I probably won't have time for the last result, but that's okay. First of all, we have theory that shows that XDO is guaranteed to converge to a Nash equilibrium in a number of iterations, so a number of policies that we add to the population that is only linear in the number of information states in the game, and not exponential as in PSRO. Because we are using that sequential nature, the drawback, the flip side of that, is that our restricted gains grow much faster. Because we are adding all action combinations, right, to the game. So iterations become much harder to solve. And now the really curious question is, okay, yeah, we need a lot fewer iterations because our restricted gains are so much more powerful, but they're so much harder to solve. Why is that working in our favor on balance? And again, we don't have a complete answer to that. More theories needed, more analysis of the kind of Nash equilibria that we had. We know that Nash equilibria can be supported with very few policies, but how come we are able to find those few policies? It's not really clear, but here's some intuition. So XDO really allows you to mix the best responses in the population in every step, in every action you take. PSRO works only in the matrix form, so it just mixes between best responses just once. You can think of it as mixing at the start of the game and then keeping the same strategy, population strategy for the entire game. And so that's just a weak play, right? Because it may be possible to infer which selection you made, and then just you're becoming predictable. But we're mixing in every step, in every action. So we're not as predictable. We're effectively allowing exponentially many combinations of our best responses because we're allowing to remix them in every step. Now, the intuition here is that if we add a best response, presumably all the actions that it can take are of interest sometime, are possibly of interest for the Nash equilibrium, for the final solution. And so even though we're adding all these combinations of different actions, hopefully many of them tend to be actually interesting, and we're not just adding exponentially many combinations to make our game harder that are not useful. Hopefully they are useful. So that's the intuition here. And so even though, what we're doing is we're making the opponent much harder to beat in every iteration. And so we improve much faster. Okay. That's a different work that I wanted to talk about, but we're sort of out of time, so I'm going to skip that. I'll just go to the takeaways. So generally, our algorithm is better and the agent improves faster, the better we make our opponent. The better when we best respond to a better policy. So how do we go about best responding to a better policy? Well, we can best respond to just the current policy of the agent, but it's probably better if we average past policies and not just the current one. And it's better if we mix them in an intelligent way that gives more weight to actually good policies. And it's even better if we allow that mix to be sequential, to keep the sequential structure of the game. And this is the other work that I did not have time to talk about. So with that, I would like to thank all the awesome people who are working on these projects: Lithian Liang, Yaoshen Xu, Deling Hu, Alex Eiler, Peter Beal, Stephen McAleer, who recently graduated and has done a lot of this work in game theory, Jay Bielmir, Kevin Wang, Mark Langto, and Pierre Baldi. And thank you all for listening. Any questions?
Okay, let's all virtually thank Roy for a great talk. Yes, if we have any questions, feel free to just, I think we're a small enough group, you can unmute and ask. You could also put your question in the chat if you'd like. So this is probably a little ignorance on my part, Roy. Could you explain a little bit in the context of this last project, what the difference between a mixture and what you called a sequential mixture is? Like what does that mean in that context?
Sure. So let's take, for example, a poker game, right? And let's say I have a population of past policies that I use to play poker, right? One thing I can do is I can, we're going to play another hand of poker. I can mix over one of my past policies, pick that one, and for that entire hand, the entire betting sequence for that hand, I just stick to what that policy did, right? So that's mixing at the beginning of the game. Alternatively, what I could do is anytime it's my turn, I can go back to my population and say, okay, I'm now going to have another mixture over my population strategies. That gives you a lot more flexibility. And it also makes you a lot less predictable, right? So even so in the first case, someone could figure out, okay, yeah, I know which policy they're using. From that point on, they're just predictable. They're just deterministic. But if I keep mixing, now I'm not predictable.
Okay, that makes sense. Thank you. Any other questions for Roy?
I have a question. I know we've kind of talked about these topics, but maybe trying to make a connection between the first part and the second part. Where do you see future work in these areas of soft reinforcement learning combined with game theoretic methods?
Yeah, absolutely. Well, we discussed this, right? Yeah, so we had this also work with Yannis that kind of shows that optimization algorithms for multi-agent problems can sort of benefit from softmax representations, right? And so I don't quite know how exactly that connect in the end, but the way I see it, we're talking about variance in just reinforcement learning. And here, when you have multi-agent, intrinsically you want to be stochastic, right? So intrinsically you want to have a distribution over actions to be less predictable to the opponent. And that kind of connects with some of the ideas we had there for how to reduce the variance using softmax operators. So I don't think that was very clear, but yeah, there's a lot of connections there.
Okay, well, great. Thank you all for joining us. We're off next week for the Martin Luther King holiday, but we should be back in 2 weeks with another virtual talk, and I hope to see everybody there.
Thank you.